I should start. I'm just sitting here chatting with people in the chat thing. Oh, I should turn the music down too, so you can actually hear me. Welcome back to Chem 140. It is week 9, which means that there aren't that many weeks left, so there's only a handful of stuff left to go over and to do, really. So just a agenda for this week's, like, what's coming up. As I eat my grapes here, that was bad timing. This week on Wednesday, we're going to do lab number 4. And if you look at the calendar next week, you'll notice, hey, there's Thanksgiving. Is there class on Wednesday or Thursday? No, the college is closed. So there will be no class on Wednesday or Thursday next week. Likewise, normally your lab is due a week later. However, in this instance, that would mean you'd have to turn something in on Thanksgiving. I'm not going to make you do that because that seems wrong somehow. So it's going to be due in 2 weeks instead. It will be due week 11. Okay? This should all be in the syllabus, so just double check the due dates for that sort of thing. But when I post the assignment, it will say a due date. So please don't email me saying, I can't do it. It's Thanksgiving. I am doing turkey stuff. Because I will just laugh at you and then tell you, like, it's not due this week. Okay? So just be mindful of that. There will be another quiz for not just Unit 13, but Unit 13 and 14 put together. Unit 13 is pretty short, but the calculations are pretty involved. And we're going to do that today. So that's the whole point of today's lecture, is to discuss how exactly do we find formulas of things. Like, this is sort of ancient history at this point. But as early as, like, the 14 or 1500s, people didn't really know what chemical formulas were. They had general vague ideas of, like, oh, this thing probably contains oxygen. Oh, this probably has carbon in it. For a long time, people thought water was an element because it's just so stable. But then you could break it into hydrogen and oxygen, and they're like, whoa. It took a long time and a lot of different calculations to get to the point where people had enough information to work with to determine chemical formulas. Maya, we've talked about this. No, don't come here. Come on. Just ignore her. Maya, go away. I don't have any water to spritz her with. I drank it all from my cup. Okay. I'm just going to pretend she's not there. All right. We're going to start with this definition here. The empirical formula of a compound is the simplest ratio of the elements in its formula. Now, what does that mean? What that means is that you cannot divide out a number from the formula. So, for instance, if I wrote down this formula, C2O4, I could divide each of the coefficients by 2. To get this formula. This formula right here on the right, I cannot reduce any further. There's no number that both coefficients, this 1 here that I didn't write, and this 2 here, are divisible by. So this is an empirical formula. Now, the number we're dividing by has to be an integer. So, for instance, this right here, yeah, you could divide by 1.5, but if you did that, you would get this. And if you do that, you end up with a fractional atom. There aren't halves of oxygens flying around. You can't do that. So this is not allowed. You cannot end up with a decimal as a result. What that means basically is that sometimes you'll have formulas where you don't have a 1 in the formula somewhere, but you still have no number you can divide by. So this is also an empirical formula. This right here, C2O4, is not empirical. Why did it stop writing? That's interesting. I mean, it sees that my pen is there. What is going on? Oh, no. Okay. I don't know what's going on with my tablet, but It just suddenly stopped writing. I mean, it recognizes that it's a tablet. Is it working now? Now it's not even... Oh. Why? Why is this a thing? Grumble, grumble. Okay, hold on. Let me try this. So I'm going to unplug the tablet. I'll plug the tablet back in. And then... That's exactly what I wanted to happen. Oh, well. I don't understand. Oh. Oh. Okay, we're going to assume that that works. Sorry about that. Wait, why can't I interact with this? What is going on here? Oh, that's just what I want to see, is the swirling blue circle. Microsoft PowerPoint is not responding. We're going to do this really quickly. And I'm going to see if I can fix it. This is exactly how I wanted my lecture to start. How about you guys? Where is Unit 13? There it is. Oh, good, the other cat has come in to start yelling at me. Just what I wanted. This is great. Alright, let me see here. Okay, that works. That works. And that works. Okay, great. Yeah, that's fine for now. Okay. Alright, apologies for that. So, on the board here, I have... Let me get the highlighter out if I can actually... There we go. So this formula that I've highlighted in yellow could be an empirical formula. And the reason that's an empirical formula is because there's no number I can divide out of it. Now, the green formula is not an empirical formula because the common denominator between those two coefficients is 2. So here's a bunch of formulas here. What I want you to do is tell me which ones are empirical formulas and which ones are not. And if something is not an empirical formula, divide out the coefficient so that it becomes an empirical formula. So for instance, the first one, N2F3 would be an empirical formula, yes, because there's no number you can divide 2 and 3 by to get whole number coefficients. Like if you divide by 2, you end up getting a 1.5 for the fluorine, and you can't have half a fluorine. If you do, the PowerPoint presentation explodes, and everything falls apart. I don't think I've ever had PowerPoint crash before. Like, not at work, not at home, ever. I just rebooted my computer, too, so... No, there's some answers coming in, so that's good. Let me know your predictions in the chat. All right, for this first one here, is there a number I can divide both of these by? I already have a 1 here, so no. This must be an empirical formula. For this second one, I got some 2's here, so I'm going to divide both of them by 2. And what I end up getting is HO. Now, note that this is not hydroxide. Be careful. Hydroxide would be a minus charge on there. The order of the elements doesn't really matter. But the minus is very different in this case. So this is a neutral compound, and this is an ion. For barium nitride, I have 2 numbers that there's no divisible factor between. So this must be an empirical formula. I don't have a number I can divide both by and get a whole number. For this one, I can, again, divide by 2. I get HCO2. And there you go. Now, you're not always going to divide by 2. You might divide by 3 or 4 or even more. In fact, later on when we do problems in this unit, we're going to divide by decimals to force something to be a whole number, and then get to the empirical formula that way. Now, I don't really remember if my slides talk about this. Let me just look through them really quickly here. Yeah, they don't. I talk about this in 161, but I'm going to go to this right here. And that's fine right there. Oh, Steve is messaging me again, because everybody has to bug me during my lecture. To be fair, something did happen that is important to both of us, and so he was talking about that with me. I want black for this. Okay, so why do we care about empirical formulas? This seems like a kind of a trivial thing, like, whoop-de-doo, I can reduce this into this. Who really cares? And the answer is, the reason that we care about empirical formulas is because it's sort of an abstract way of seeing what molecules look like in terms of the precision that we are able to get. So, for example, let's suppose that I had a molecule, and the molecule could be this, it could be this, or it could be that. It could be one of those 3 things. All I know is it has nitrogen and hydrogen in it. So what I'm going to do is I'm going to tear the molecules apart that I have. And again, it's one of these things. Now, if I had one molecule to tear apart, and I said, okay, here's the N bin and here's the H bin, I could go, let's get a larger, let's do that. Okay. Oh, no, that's too tiny. How about that? That's better. Okay. All right. Let me get a color that's appropriate for nitrogen. There we go. Okay. So I could go doot. Or actually, you know what? Hold on. Back up. We'll start here. Let's suppose that I broke apart one molecule. And this is what I found. And you would immediately go, oh, well, I know it's not this, and I know it's not this one. It must be N2H4 because there are 2 nitrogens and 4 hydrogens. That would be really easy. However, in reality, we can't just grab one molecule. If I, take a spoon and scoop into this bag of nitrogen-hydrogen amalgam, or whatever it is that we have, I'm going to get tons and tons and tons and tons of molecules. What my sample's going to look like if I decompose that is this. Doot, 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 doot. Of course, it's not working now. Oh my goodness, everything is the worst. Why? Why is this a thing? Yeah, it's not even letting me draw with my pen. What the heck? Select all. Okay, there we go. I bet I had the eraser selected. I'm an idiot. Okay, so if I were to decompose lots of molecules, I would get something that looks like this. And ignore that they're not all the same size because I'm just not tapping the thing hard enough. So maybe that's what my nitrogen side looks like. And I gotta count these. 3, 6, 9, 12. Okay, so. All right. I have split apart an unknown number of molecules here. And what I would find out from this unknown amount of molecules is that I have twice as much hydrogen as I do nitrogen. Because I could just basically say, okay, that's roughly half. So by decomposing a ton of molecules, I would then see the ratio between them. And I could go, okay, I must have some molecule that has the empirical formula NH2. So what that means is that when I go up to here, and I'm trying to figure out what my molecule is, I can immediately eliminate this one. Because that would have a 1 to 3 ratio, but I've observed a 1 to 2. However, I cannot differentiate between these two things. So I know my molecule is one of those two things. Now, I'd shown you at the start, this is the one that I was picking. So what empirical formulas represent are a family of molecules that represent just the ratio of atoms, because when we examine molecules, to the best of our ability, in order for us to figure out what the ratio is of elements, we have to tear apart a bunch of molecules by basically putting a ton of them in a container and heating them until all their bonds break. Unfortunately, you can't do that with one molecule because we don't have molecular tweezers that are tiny enough. But when you do it with a lot of molecules, you can get the empirical formula out, and that's why we care about it. All right. Now, how do I relate the empirical formula to the actual formula? The actual formula of a molecule is called the molecular formula because it's what the formula is for the molecule you're looking at. Now, the relationship between the empirical formula and the molecular formula is given by a multiplier, and the formula for that is to simply just say, okay, what number do I have to multiply by in order to get the molecular formula? So in this example, I have an empirical formula, and I multiplied it by some number. What is that number? Yeah, obviously it's 6, right? Yeah, easy enough. So this is just the process backwards. Now, if you want to find the formula of something, it's easy to find its empirical formula. Finding the molecular formula is a little more difficult, and we're going to do that in the next section by doing this process and adding a step to it. Excuse me. All right, so here's how we figure out the formula of any substance by determining the ratio of elements. Okay, so the first step is to get a sample and then find out what the mass composition is. Remember how we did percent mass composition? We're going to do that more or less here. We're going to reduce our substance down to, okay, I have this many grams of each element. Yeah, Unit 13 is basically applied Unit 12. We're going to figure out the mass of each element. Then what we're going to do is we're going to take those masses and we're going to turn them into moles. Because moles are a counting measure, right? If I have 1 mole to 2 moles, the ratio is 1 to 2. So figuring out the number of moles we have will tell us what the ratio of elements is in our formula. Finally, what we're going to do is we're going to manipulate the numbers so that they become a formula. And there's some shenanigans that we do with that too. All right, so let's do an example of this so that you can see it in action. Because this process it looks kind of complicated and there are a lot of steps, but when you do a bunch of these, it becomes very trivial. All right. So I'm going to give you Freon. Freon is a refrigerant. Freon is what's known as a chlorofluorocarbon. And we don't use Freon anymore. We used it a lot in like the 50s and the 60s for refrigerants. The reason we don't use it anymore is because it goes up into the atmosphere and it reacts with ozone and decomposes it. It's actually a catalyst. So you might have heard about the ozone hole, and then the eventual Clean Air Act that followed in the 70s. This is because of Freon. Freon was one of those gases that was just like, wow, this could destroy all life on Earth. And everybody came together to like fix it. They're like, okay, we cannot use Freon anymore. This is banned. And the ozone hole actually recovered, and the ozone layer, which is responsible for getting rid of most of the UV radiation from the sun before it hits the Earth's surface, actually recovered and grew back, more or less. Okay. So if you're looking out there and thinking, man, we can't do a damn thing about climate change, look to the Clean Air Act and the ozone hole. That's proof that we can do something. That's your little bit of hope for 2020, right? All right. So I have the following composition by mass, and I want to figure out the empirical formula. So let's go over here, and I got to reformat this box here. There we go. All right, goodbye, empirical formula. All right, let me scroll this up so I can see it. All right, so I have a sample of Freon 12, and it has this mass composition. It's 9.933% carbon by mass, 58.63% chlorine by mass, and 31.44% fluorine. Now, you know how to determine these percentages. You could use the molecular masses of all the carbons and all the chlorines and all the fluorines, and then the formula mass of the molecule. But I have not given you that information, so instead I have given you the percentage. What we're going to do is we're going to take some mass. We'll say X. I have X grams of Freon. And what I'm going to do is I'm going to multiply that by one of these percentages. Remember, we can write a percentage as a ratio. I could say, for every so many grams of carbon coming out of grams of Freon, I didn't actually mean to hit that button. There we go. I could then write this ratio. And then these would cancel, and I would be left with grams of carbon. Now, what is the ratio of grams of carbon to grams of Freon? Well, in 100 grams of Freon, there would be 9.933 grams of carbon. And so I would just get whatever this number is times whatever mass I had chosen to examine for this problem. Now, you might be looking at this and thinking, well, okay, what mass should I pick? Is there an easy number to pick? Well, I'm going to do this for you. What if I had picked 100 grams to start? Well, then this number would cancel out with this number, and the mass that we would work with would just be the percentage, right? So if we assume a 100-gram sample of Freon, then in that 100 grams, we must have 9.933 grams of carbon, 58.63 grams of chlorine, and also 31.44 grams of fluorine. Now you don't have to do any dimensional analysis. We'll just start here. Okay, so that's step one. Figure out the mass of everything that you have. We're all set. All right, so now that we know the mass of everything, we need to make this into a formula. And formulas only can be formed when you know the number of moles. So we're going to turn each of these three things into a number of moles. So let's start here. We'll do the dimensional analysis. I'm going to turn grams of carbon into moles of carbon. Cancel the units out. That's what I want. Now we can do the numbers. How many grams of carbon are in a mole of carbon? Where do I get that information? Periodic table. Perfect. There you go. And then you grab your calculator and punch it in. Oh my goodness. My undo key just randomly doesn't work. Because with everything else broken on my computer today, why wouldn't that work? All right. This should be a decimal point. Let me make this eraser smaller. There you go. All right. Now we've done that, we're going to do the same thing for chlorine and for fluorine. So, grams of chlorine, moles of fluorine, or of chlorine. In 1 mole of chlorine, according to the periodic table, there are 35.453 grams of chlorine. And the number I get from my calculator is 1.6537, so 1.654 moles of chlorine. What do you notice about this number up here, this number for carbon and this number for chlorine? Do you see a relationship between them? If you don't, we'll find it in a second. But you should probably be able to see that just by looking at the numbers. Like, oh, this is different. I don't know why I write Cl. This is different by some factor. Same thing for fluorine here, except I don't have this molar mass memorized. 18.998 grams of fluorine per mole of fluorine. Let me cancel the units out. And when I do this number, I get, ooh, look at that, 1.655 moles of fluorine. So the amount of chlorine and the amount of fluorine is remarkably similar. In fact, those might as well be the same. And the amount of carbon that we have is roughly half of what those are. Now, in order to do this as close to mathematically precise as possible, here's what we're going to do. I'm going to take these numbers and I'm going to make the formula with those numbers. And you're probably going to look at me like, I have never seen a formula look like this. You literally just told us you can't have decimals in a formula. And that's correct. This is not actually a formula. This is what I'm going to call the pseudo formula. So once you know the number of moles, you're going to then construct the pseudo formula. And you do that by just taking those numbers and writing them as if they were a formula. Because a formula is just the ratio of elements to each other, right? And so this is a ratio. It's just that these numbers don't really make sense from something that I could build. So I can't grab 0.827 of a carbon. So to resolve that, what we're going to do is we're going to divide all of the numbers by the smallest coefficient. And of these three numbers, 0.8270 is the smallest number. So I'm going to divide each of these by that number. And when I do that, I will then get whole numbers, or at the very least, I will get something that's really, really close to a whole number. So 0.8270 divided by itself is just 1. So for carbon, the coefficient is 1. But 1.654 divided by 0.8270, when I type that in the calculator, I get exactly 2. But when I do fluorine, I get 2.001209. What we're going to do is we're going to say that that's close enough to 2. Because molecules have to be in exact whole ratio formulas. You can't have a fraction of an atom. When you do this process, the result that you get at the end is an empirical formula. So that was our 3-step process here. Step 1, we figured out the masses of everything. Let me get a darker color here. So here was step 1 where we got masses. And then step 2, we figure out the number of moles. Why are you like this? Get down. Get off the desk. No, don't just sit there and stare at me. Oh my goodness. I'm trying to clap at him, but he's looking at me like, oh, I don't give a shit. I'm a cat. No, go away. Go. No. All right. So that's the process. That's how we determine an empirical formula. Where did my PowerPoint go? There it is. Okay. Okay. And then this, my slides are just telling you how to do this. This is the process that we did. Oh my goodness, you're a different cat. Where that? Oh my, what is wrong with them today? Did I forget to feed you or something? What I'm going to have you do is I'm going to have you do the same process that we just did while I check to see why my cats are, like, being so needy right now. So I've given you this mass percentage data for, I believe this is a pesticide. So what I want you to do is tell me the empirical formula based on the steps that we just did. And we'll go over the answers in just a moment. All right, I'm back, and of course they needed nothing. They just wanted to. They wanted me to pay attention to them. So I got the squirt bottle because this is now a thing we have to do. They will receive a fine misting of water. So that's the right formula because I have this one memorized. I don't actually know what this is. Let me look it up, actually. C13H18. C9. Oh, it's not a pesticide. It is an antidepressant. I think it is an antidepressant. Yes. I want to say that this is oh, what is it called? Brand name. Wellbutrin, that's what it is. And I believe that I know people who take this medication. So I'm going to give just a few minutes for people to finish doing their calculation to see if they can get the correct answer. And then we'll go over the correct answer together on the screen. All right, let's go over the answer here. Let me clear my screen here. And we'll just get this on the screen there. All right. Let me scroll this up. All right. So if I assume a 100-gram sample, then what that means is in that 100 grams, I would have 65.13 grams of carbon, 7.57 grams of hydrogen, 14.79 grams of chlorine, 5.84 grams of nitrogen, and 6.67 grams of oxygen. So I could turn all of these into moles. So let's do that. So in a mole of carbon, there are 12.011 grams of carbon. And I didn't actually do these numbers. I was dealing with cats. One of them has already come in and gotten squirted with water. She ran away immediately before, like, I could even point the bottle at her. 2, 3. Okay. So there's our carbon. And let me know if I make a calculation error, because I'm prone to doing that, and I want to do these quickly. All right, so here's hydrogen. You're going to notice that, oh, I only get 3 sig figs out of this one because this first number I had only had 3. So this is 7.51 mole of hydrogen. Should our answer be rounding to 4 sig figs? It depends on what numbers you're using. However many sig figs from the result. So, like in this problem, when I multiply, this one only had 3 sig figs. So my answer's got to have 3 also. At the end of the day, it's probably not going to matter because you're going to reduce these down to a digit anyway. Or a whole number, at least. I'm just writing a bunch of sig figs for these molar masses because these are the numbers I have memorized. Like, it takes me more brain power to actually not write the last number. 4172 moles of chlorine. Grams of nitrogen, moles of nitrogen. And I get 0.4169. You'll notice that that number is quite close to the number we got for chlorine. And then grams oxygen, moles of oxygen. 1 mole of oxygen, 15.999. And that number is the number we got for nitrogen. All right, so I'm going to scroll this down a little bit, and I'm going to write my pseudo formula. So I got C 5.423, H 7.51, Cl 0.4172, N 0.4169, O 0.4169. I'm going to then divide by the smallest number, which would be one of these two. That should be a 0 there. Let's just try that again. And when I do that, 5.423 divided by 0.4169 is 13.0079. That's really close to 13, so I'm going to keep it. 7.51 divided by 0.4169 is 18.013. That's really close to 18. And then Cl and O are all 1s. And there you go. There's our empirical formula. Now, for really complex molecules with weird ratios like 13 to 18, the empirical formula is almost always going to be the molecular formula. It's very unlikely that the actual formula is this with all times 2. But how would you definitively determine that? And what we're going to do in the next section is talk about the next step to this process, which helps us determine what the molecular formula is. Now, the physics behind what's going on is, we're simply weighing molecules, because we can do that. We can't grab them individually, but we can weigh them more or less individually by firing them through a magnet. And that's called mass spectroscopy, which we're going to talk about in a lot more detail in 161. But suffice it to say that we can weigh molecules. So if I know what the molecule weighs in AMU, I can look at what the empirical formula weighs in AMU and figure out the multiplier. So when we get back from our break, that's what we're going to do, is we're going to move in that direction. So I'll put the title card up. Let me get live split on the screen here. We'll start the timer. And we'll put some more Stardew Valley music on because it's awesome. See you in a bit. was so close. I don't know if I've landed exactly on it this quarter or not. I did once last quarter. Okay, so just really briefly, since it's still kind of in the middle of the break here. I don't know what I was going to say. I was going to talk about Stardew Valley, that's right. Just in case you're curious about some of these games that I play music for, Stardew Valley is a farming game. I grew up on a farm, like I am actually a farm boy. Central Valley, California is just all farmland, and that's where I'm from. Farm games are a little faster than actual farming, but they're still fun. It's a good chill out game if that's your shindig. Let's see here. I'm going to leave this example for you to try on your own, because we have done enough examples, and it's time to squirt bottle the cat. Yep, she immediately ran away. And I want to talk about the molecular formula. Okay? Because to do the molecular formula, we had to do everything we've already done anyway. So we're going to get more practice. Just really quickly about this previous problem, if you want to look up the answer on your own, the molecule I've given you is ibuprofen. So you can look up the formula of ibuprofen on Wikipedia, and if it has a common denominator, you can divide it out. There might be a 2 you have to divide out, for example. And you can solve it then. All right. So let's talk about how we do molecular formulas. What we're going to have to do is we're going to have to weigh molecules. If I know the molecular mass in grams per mole, and I divide it by whatever the empirical formula weighs, the empirical mass, also in grams per mole, the units cancel out, and what I get is my multiplier. For example, if the molecule was just double the empirical formula, it would also have double the mass, and so I would have 2 times some mass divided by that mass, and those masses would cancel out, and I would get a multiplier of 2. So when you do the empirical formula process, at the very end you will get an empirical formula. You can then figure out the mass of that empirical formula in grams per mole, and that number goes on the bottom of this expression. The mass of the molecule goes on the top, and I have to tell you that mass. Like, a problem might be, determine the empirical formula, and then if the molecular mass is 79.8, what is the molecular formula? Something just like that. So that's what we're going to do. There's the formula again, in case you wanted it printed a little neater. All right, let's do an example. Let's suppose that we did the empirical formula already, and I found out that the empirical formula of my compound is this, CH. And then I read the problem, and the problem says, okay, its molecular mass is 78.11 AMU. Remember that AMU and grams per mole, same thing. So what I need to do is I need to figure out the empirical mass. And that's just carbon and hydrogen added together. So it's going to be 13 something, but let's get a few more sig figs. 13.019 is what I got. Yeah, I get to keep all those from this periodic table. So if I have CH as my empirical formula, and something that is 78.11 grams per mole as my molecular formula, I could divide those two masses. Oops. We'll just do that. Like this to get my multiplier. And I should get 6 when I do this, but I'm going to type it in my calculator anyway. 5.99996. Okay, so yeah, that's 6. So if the multiplier is 6, I'm going to take my formula and I'm going to multiply it by 6 to get this, and this is benzene. So the formula of my compound must be benzene, C6H6. So this extra last step helps us figure out molecular formulas. And that's something that you'll have to do depending on whether the problem asks you to do it or not. All right, let me clear all that and put it on the screen here in text. And then we'll give you one to do here. So I'm going to give you... Oh, where did the 13.09 come from? So that was the mass of the empirical formula. So the empirical mass here was 13.019, because that's a carbon and a hydrogen added together. That's what that weighs. And then when you do the empirical formula mass on the bottom of this expression divided by the molecular mass, you then get the multiplier. Cool. All right, so I'm going to give you butane dione. Let's suppose I have some sample of butane dione and I decompose it into these masses. What I want you to do for step 1 is figure out its empirical formula. And then step 2 is, well, let's suppose that the molecular weight of the formula is 86.09 AMU. Well, would its molecular formula be? Okay, so first type in the empirical formula in the chat when you get it. And then type in the molecular formula and the multiplier once you get to that point too. Okay, so I'll give you about 5 minutes to do that. We'll go over the answers in just a bit. All right, I see some answers in the chat. Let me prepare the this thing. Whatever I want to call this, my like whiteboard. We know we're going to determine the empirical formula and molecular formula, so I'm going to just chop that part of the problem off the screen so that we can have more space to work with. So we're going to start by finding the empirical formula of this compound. So I gave you 27.90 grams of carbon, 3.512 grams of hydrogen, and 18.59 grams of oxygen. So, same process we've been doing all along. We're going to turn grams of carbon to moles of carbon. And I should probably turn on my calculator before I start typing into it. I'm just blindly typing in numbers here. 2.323. I immediately just started typing in the calculator. I didn't even write the number down. All right, so how many moles of hydrogen do we have? 3.484. And then for oxygen here, wow, it's really windy outside. It's just blowing in my window. We have some weird weather today. It's super warm. 1.162. So there's our pseudo formula. I just got to actually put it into the form that we're familiar with. There we go. It's a little crowded over there. Let me see if I can neaten that up a bit. Oh, that's too tiny. Boop. 1.162. That's even more crowded, but oh well. We're going to divide by the smallest number, which is 1.162. And the first coefficient for carbon becomes C2. H3, and then O. So that's the empirical formula. And yeah, I actually try and pick molecules that are real when I do these examples. Like, I make most of these problems up, or I source them from other textbooks. Mostly because then we can have conversations like, hey, artificial butter is delicious. What is it? Oh, here it is. So I don't know how many grams of butter this sample would be. Let's see here. 45, 48, like 50. 50 grams of butter. Actually, that's not very much butter now that I think about it. All right, there's my empirical formula. Since we're going to need it in a second, let's figure out what the empirical mass is. And so if I take my calculator and I do 2 times 12.011 plus 3 times 1.008 plus 1 times 15.999, my calculator says that the empirical mass is 43.045 AMU, or grams per mole, whichever. You could also have gone to Lentech to do that. That would have worked. You'd get 43.05, I assume. All right, so now let's do the molecular formula. I actually need to extend this down again because I don't remember what I assumed is like 86 or something, but I didn't know the exact number. So now, if the molecular weight is 86.09, what is the molecular formula? So remember that to figure out the multiplier, the formula to do that is the molecular mass divided by the empirical mass. And so that would be 86.09 divided by 43.045 that we calculated. And that's got to be 2, right? So when I take my empirical formula and multiply it by the multiplier, I get C4H6O2. And that's the molecular formula. There you go. That's how you do it. Any questions on how we do empirical and molecular formulas? I hope I hit mute before I sneezed. Otherwise, I apologize. All right. So let's go on to the next problem, which is how do we actually do this? Like, what I have shown you is great on paper. How do we realistically decompose something and just say, okay, here's all of its carbon, here's all of its oxygen, here's all of its nitrogen, etc.? And the answer is that there's not really a reasonable way to do that. What I have shown you is an idealized sort of model process. We can't do that in reality. In fact, when we get a sample of stuff, like if I handed you butane-dione, and I said, tell me what's in this, the way that we actually analyze samples is we combust them. We ignite them. And yeah, you burn it. That's basically all that you do. So what I'm going to do here is I'm actually going to show you how this works. Since I don't think I have a diagram, but I actually did elemental analysis in grad school. So like I know all about this process because we had to ship our stuff off to a company that did this for us. And then I took a class on what the company was doing. And I was like, that seems really easy. Why don't we just do this ourselves? And the answer is it requires really high precision equipment that's extremely expensive to both acquire and maintain. So a company had already acquired that. So here's our sample. Our sample is going to be green for no reason other than that's the color I've selected. What you're going to do is you're going to take your sample. We're going to put it in this bin that is connected to a series of filters. And then out here is exhaust. So what's going to happen is you're going to ignite the sample, and we pass oxygen in to do this. And then all of the combustion products are going to go in this direction. And they're going to go through this series of filters. I should probably make those different colors, but that's okay. All right. Now, whenever you combust something, you generally get this as a result. So if like X was chlorine, you'll get some sort of chlorine oxide. The only thing that this doesn't really work with is fluorine. You get something different that way. But there are other ways to deal with fluorine. Oxygen is very, very reactive. It likes to oxidize things. You might have heard of the process of oxidation. This is a process by which oxygen takes the electrons of things and then forms either covalent or ionic bonds. Specifically, when I combine a substance that has carbon or hydrogen in the compound, then what we end up seeing is, well, with that X plus O2 thing there, if X was C, I'd get CO2. And if X was H, I would actually get H2O. No, we're not playing Among Us. We're talking about combustion analysis. This is just sort of a like how-to, just in case people are curious. Like if this is me talking to future you just skip ahead a few minutes if you don't give a shit about the theory, and that's okay. So if I have a compound that has only carbon or hydrogen in it, and I combust that with oxygen, the products that I get are always going to be carbon dioxide and water. Now, next quarter, we're going to do an example where we have oxygen in there also, and I react it with an O2. This is a Z, by the way, or a Z. Sorry, my Canadian came out. So that's the letter Z, and this is the number 2. Just in case those look similar. Whether your compound has oxygen in it or not, you get the same result. You get CO2 and H2O. Okay, so now that I know that those are the products that I'm going to get from my combustion, how the heck do I figure out what's in there? Okay, well, my sample has... Let's suppose that it's a hydrocarbon. It's got C and H in it. So when it combusts, I'm going to make CO2 and H2O. Up here at the top, I have a series of traps. And what the trap does is it traps the compound that it's specifically selected for. For example, the water trap is like a desiccant. It absorbs any water that passes through it and traps the water in that region. So I start with CO2 and H2O. All of my H2O gets stuck in here, but the CO2 gets to keep going. Then all of my CO2 gets stuck in here in the carbon dioxide trap. And what comes out is just excess oxygen or air or whatever exhaust is flowing through this to keep it all going through the system. Then what you do is you disconnect the trap here. And you just go weigh it. And the weight difference before and after is how much water you have obtained. Now you might think, okay, well, learning how much water I have in my sample is not super useful. But consider the following. If all of my hydrogen in the combustion analysis ended up in water, and I know the number of grams of water I have, I could turn that into moles of water, and then moles of hydrogen. And then make the pseudo formula out of it. Because I know all the hydrogen that's in that water came from the original sample. So this is just a roundabout way of finding the mass of the hydrogen and turning it into moles. Instead, we're going to use the mole-to-mole ratio to do that. Same thing with the carbon. The carbon completely ends up in CO2. So if I know the mass of carbon dioxide, I could figure out the number of moles of carbon dioxide. And that'll tell me the number of moles of carbon. And then I can do the process we did before. So what we're going to do is we're going to do a really simple example. I have an example with oxygen, but that case is much more difficult. We're going to leave that for next quarter. Because I don't think the hard examples are in the supporting text, and I'm not even sure if they're in the OER text, but we're going to do one of these examples right here, where it's just carbon and hydrogen. And when we do that, we're actually going to see a special edge case that comes up with any empirical formula, potentially. Okay. So this sort of serves a double purpose. All right, so here are the process steps that are required for doing combustion analysis. How do you know if we are doing combustion analysis? The problem will talk about CO2 and H2O. So if you read a problem and it immediately starts talking about water and carbon dioxide, you're doing a combustion analysis problem. So here's how we do this. The first step is to burn your compound and you get H2O and CO2. Generally speaking, the problem statement will have done this for you. They're going to tell you, oh, I made this many grams of water and this many grams of CO2. Now solve the formula. Once you know the amounts of H2O and CO2 that have been made, turn it all into moles, just like before, and then use the mole-to-mole ratio to figure out the number of moles of hydrogen and carbon, and then you can make a pseudo formula out of it. So this process is similar to what you did on the previous problems. You just are starting in a different place. So let's do an example of this. I'm going to burn a hydrocarbon. Whenever you hear the word hydrocarbon, you should think, okay, hydro, that's H, and carbon, that's C. Now, as an aside here, there's another word that's similar to this, carbohydrate, where carbo is your carbon, but hydrate is water. So a carbohydrate has carbon, hydrogen, and oxygen in it. But a hydrocarbon has only carbon and hydrogen. So this is just where these terms come from, in case you were curious. They get thrown around a lot in chemistry and biology, and I know a lot of people taking this class will be doing biology. So just some information that might come in handy for you as you continue to learn the jargon. All right, what is the empirical formula of this compound? So let's go back here. That's not my, whatever this is called, Photoshop. I gotta get back to this window. All right, so I'm going to write down the masses that I was given here. This is CO2. And that's water. So I'm going to write down the unit map just for our general process here. This will be for CO2. So I started with the mass of CO2. We're going to turn that into moles of CO2. And then moles of carbon. Okay, so let's do that. Mass CO2 turns into moles CO2. And then moles of CO2 turns into moles of carbon. All right, so when I'm done with this calculation, I will have the moles of carbon, which I can then enter in the pseudo formula. Okay. How many mole, or in 1 mole of CO2, how many grams of carbon dioxide are there? Well, you would just go to Lentech and punch that in, CO2. This one I have memorized because I did a lot of combustion analysis. 44.01. And then over here, how many moles of carbon are in a mole of CO2? So in one of these big things, how many C's are there? Remember this from chapter 12? Now you're seeing why we do this, I guess. Yeah, it's just 1, right? Because the formula coefficient is 1. So how many moles do we got here? 1.83 over 44.01. And I have 0.0416. All right, let's do the same thing with hydrogen here. So I'm going to turn grams into moles. And we'll turn moles of hydrogen, or water, I'm sorry, into moles of hydrogen. And I'll do that one down here so I have a little more space. All right, same thing as before. Molar mass of water is 18.02. And then the ratio of water to hydrogen is 1 water molecule has 2 hydrogens in it. And it looks like you're going to get 0.1 for the answer. Let me punch it in the calculator. Oh, I'm going to get exactly 0.1, aren't I? Yeah, okay. Different color. Okay. Now, we've done the steps correctly, but you're going to look at these numbers here and be like, I don't immediately see a number I can divide out. But let's do the process anyway. I'm going to divide by the smallest number. And I will get C1H1 over 0.0416. Oh, sorry, I made a mistake. Thank you. Not 1 here. 0.1. I actually was typing out my calculator incorrectly as we speak, so I'm glad that you pointed that out quickly. All right. And here's what I get. I got C1H 2.4038. I'm actually going to write out all the numbers here because what we're going to do is we're going to look at this and go, there is no real good rounding that I can do here to get to a whole number. Like, I can't round this to 2. I can't round this to 3. What should I do? And the answer that we're going to do is we're going to try and find a fraction that resembles this number. First of all, I'm going to chop off some numbers so that I get something that looks like it could be a fraction here. For example, I could write this like this. Right? And don't worry, I'm going to show you a better process than this right here for how you deal with these weird edge cases in a second. But let's suppose that I wrote this number, 2.40, as this fraction. If I wanted to clear fractions, I could multiply everything by the denominator, right? First of all, let's make this an improper fraction, 24 over 10. And then I'm going to multiply both numbers by 10 to get rid of this. So 10 and then 10, and those would cancel. I'd get this. Now I can divide by a number that both divide into. And I get this, which is an empirical formula. And you might be looking at that and going, what the hell? And I put this example in here specifically because you get this bizarre edge case number. In some circumstances, you will get a fraction for your empirical formula when you do the math. And that's just a result of how math works when you're doing this process. When you divide by the smallest number, you inevitably force something to be 1. But not all empirical formulas have a 1 in them. If you do that, the other number will be a fraction. And so what you need to do is you need to be able to undo that fraction. The way that you can do that most easily is by looking at your decimal and trying to express it as a fraction. Where did the over 2 come from? Which 2 do you mean? Do you mean this 2 right here? Or do you mean this 2 down here that I divided by? Oh, that 2 is just... So this one right here, this is me dividing by a number to get to the empirical formula. Because there is a number I could divide both of them by, and that number was 2. Kind of like the first thing we did today. Is this an empirical formula? No. But if I divide up both of them by 2, it is. So what do you do for these edge cases? And the answer is you want to look for fractions. So for example, 2.4 is the same as 2 4/10, which equals 24 over 10. That's a fraction, and now you can clear it by multiplying both numbers by the denominator. Another example would be if you got 1.5. That's the same as 1.5 or 3/2. You could clear that fraction by multiplying both of the numbers by 2. So let's suppose you got this as your empirical formula. What fraction would you represent the h as? Like, what is 0.25? That'd be 5 over 4. Yeah, very good. CH 5 over 4. I could clear that fraction by multiplying both numbers by 4. And that would be my empirical formula. Why did we divide by 10 again? I am trying to make this number into a fraction. 0.4 is the same as me saying 4 divided by 10. You could also write it as 2 divided by 5, and then multiply everything by 5. Let's do another one. Let's suppose that you had CH 1.33. That would be like what fraction? What is 1.33 as a fraction? And you can put more 3's in there if that helps you make up your mind. Yeah, very good. It'd be like 4/3, right? So now I'll multiply both of those numbers by 3 to clear this denominator. And this would be my empirical formula. So if you end up on an edge case, and what I mean by an edge case is you get a number that looks like a fraction. Turn it into a fraction and then clear the denominator to get the empirical formula. Now, what sorts of cases are not edge cases? Those would be things like this, where you do the math and you get something like that. Generally speaking, if you can round to the whole number or to the fraction, do that, and that's good enough. For our purposes, usually only the first 1 or 2 decimal points are going to matter. And if you're off by like 0.1 to a whole number, take it as the whole number. Or I'm sorry, not 0.1, but 0.01 to a whole number. So like if you got 1.99, that's 2. But if you get 1.8, don't round that far. Look for a fraction and see if you can get a better empirical formula. Yeah, the chat seems kind of slow. I don't know if it's just YouTube or if an option got detoggled. Do I have ultra low latency mode? I do, so it should be super fast, but super fast is kind of in the eye of the beholder, I guess. All right, so that's how we do combustion analysis. And also how we deal with these edge cases. So I think we have time for one more problem here. That's the actual PowerPoint file. I want the slideshow. There we go. All right. This slide is going to talk about how to deal with if you have another element that is not carbon or hydrogen. We're not going to cover that in this class, so I'm just going to put a big X through these slides because we're not going to deal with them. I'm not going to test you on them. We're going to deal with that in Chem 161 just because this is a whole extra step that we had to add onto this ordeal. And I would rather give you and the only practice problem I have has CH and O in it. Okay, so my worksheet should have some example problems on there. And I'll look at the worksheet and make sure that I have enough for you to practice on. You're only ever going to see like one combustion analysis problem in this class, and it'll be on the quiz, and you'll see virtually the same problem again on the final, because I only have so many of these with carbon and hydrogen. So as long as you can do this process, do the practice problem for pentane again, the C5H12, and then look at the worksheet and see if there's one that's just C and H. Do that one too, and if you can do those, you're in good shape. The most important problems for all of this combustion analysis that you can do, or not combustion analysis, for empirical formulas, are the stuff from the start of Unit 13, where I give you like a percent, and you figure out the formula that way. That's more important. This is more just sort of like, hey, this is how far the rabbit hole goes. We're going to do that next quarter. Okay. But that's Unit 13, so here you go. We have to celebrate. Oh, we don't get to celebrate because I don't have any music. There you go. I got to do that, and then I can do that. I don't remember what Unit 14 is. I think Unit 14 is, it might be balancing chemical equations. I forget. That's 14 or 15. We are almost done. There are 3 units left. We have 3 weeks of class left. We're going to do Unit 14 probably mostly on Thursday. We'll definitely finish it on Tuesday next week and then start 15. We might even finish 15. And then the last week will just be 16, and then we're done. So, congratulations if you've made it this far. You are almost to the finish line. I want to thank everybody for coming out to the lecture today. If you have any questions about the material, please let me know by email. I'll be around. Something I do want to mention really briefly, I'm going to post an announcement on this soon. Course evaluations are coming out. I'm going to hit the button to release those probably within the next few days. There is a small amount of extra credit depending on how many people do the evaluations. No witch hunts. Do not force each other to do the evaluations or harass people. But the more people that participate, the more points they give you, up to 5 or so. What's a course evaluation? You basically tell everybody how awesome or not awesome I am. It's totally arbitrary. It's up to you. This is your opportunity to treat me like an Amazon product. I don't know. Great lectures. Canvas is stupid. 3 out of 5. Would not buy again. I don't know. Bullshit like that. No. Course evaluations are important, but at the same time, it's it's hard to really get worth out of them when it's hard for a student to assess what they have learned and what they haven't learned. So I use course evaluations to get feedback from you, but the numbers part I don't really care about. If you leave a comment that says in there, like, YouTube was great, but maybe you should try this, that's super useful to me. If you leave a comment that says, I love the orc that you put at the end, like, that's not super useful to me. Or if you like the music that I play during the breaks, like, not super useful. But if you have feedback for, like, actual stuff that either really did work for the course for you or really didn't work, and it's within my purvey to change it, then that's useful feedback. And so that's what I really look for is, like, hey, if you can give me those comments, fill out the comments at the end and, like, tell me in your own words, like, what was helpful and what wasn't. Okay. So then I can make changes, because we're all trying to figure this online thing out together, and who knows how long it'll go for. At least until the end of spring, as far as I'm aware. So look for that. That's coming out either tonight or tomorrow. It depends on how long it takes for it to update once I hit the button. But I have a running tally of how many people have done that. Not who has done that, but just how many. And the more participants I can get, the more extra credit I award you. Okay? So it's just a little extra thank you for being in the class. And thank you for your feedback. I bribe you with points to solicit feedback. So, all right. Anyways, thanks for watching. I will see you again tomorrow for the lab lecture on lab number 4. Have a good evening, and we'll see you then. Oh, wait, I'm not ready. I didn't do this. We have to do the stupid little music thing that I exit with all the time. There we go.